So we will have this session. I'm Professor Mohammed Olena. I will chair this session. And we will have 9 presentations. So I will introduce the first speaker, Dr. Olena. She will talk from Ukraine. She will talk about spin waves in micromagnetic rings. So please come to the floor. Thank you.
It's not. Okay. Oh, thank you so much. Yeah, good morning, everybody. Thank you very much to organizing committee for the possibility to give this talk. And I will speak about standing spin waves in permalloy micro-rings of round shape. Here you can see my lovely co-authors from Singapore and Portugal. So, why rings? Because due to their very interesting magnetic properties, this shape of nanoparticle is very popular nowadays, and it will find anticipating potential applications then. My colleagues fabricated samples. Here you can see some image of a fragment of the sample, and these are lateral dimensions here and here. My colleagues investigated these rings, these samples, by broadband magnetic resonance technique. Actually, they fabricated 2 kinds of samples. I will call them thin rings and thick rings. Thin rings are of 30 nanometers thickness, and thick rings 100 nanometers of thickness. I think that they have the same lateral dimensions. Also, as you can see, these rings are quite far from each other, then we shouldn't take into account any dipolar interaction between them. Then we investigated saturated state. Saturation was achieved due to quite large external magnetic field, which was applied perpendicularly to the plane of the ring. I will call this perpendicular geometry, or some canted case where the magnetic field is in canted direction. And we investigated 2 interesting phenomena of magnetic dynamics in such rings. This is splitting of spin wave modes under symmetry violation. What does it mean, symmetry violation? It means when magnetic field is applied not perpendicularly, when the cylindrical symmetry is spoiled. Yes, and the next also interesting phenomena, which we have observed only in thick rings, is the sound peculiarity of FMR spectra. I will speak about this later. Okay, why splitting of spin wave modes exists and why it's interesting to investigate. Splitting is actually a common feature of systems where some kind of symmetry violated and the mode in symmetrical case are degenerated. So, if there are some set of modes in perpendicular geometry, then when magnetic field is canted from the perpendicular direction, this modes should split. And actually this is a very undesirable effect because of it leads to the magnetic noise and losses. So we should know how to recognize this and how to avoid this. A little bit of history. Many years ago, about 10, even more than 10 years ago, standard spin waves were investigated in disks, the usual FMR spectra. And then 2 years ago we investigated splitting of such modes in disks, and we recognized that there is some interesting hierarchy of splitting. The first mode, this is in perpendicular direction, is only one. Then in some canting, in the case of some canting, it doesn't split at all. The next mode splits in 3, the next in 5, I can say that the next in 7. So this was observed experimentally and proved theoretically. The question is, maybe the same we have in rings, like in disks, the same picture of splitting. Why not? They have the same cylindrical symmetry. But the answer is no. Why? Because of rings and disks have absolutely different topological shapes from the topological point of view. Actually, rings are much more similar to a map than to disk. Then let's understand theoretically, analytically, what it will be. Rings and disks have different structural solutions for standard spin waves. They have different structure of boundary conditions. And as a main conclusion, opposite to disk, rings have another picture of another scenario of splitting. Every mode should split in an infinite set of modes under symmetry violation. Now, what we have in experiment. Of course, theory is right, so experiment shows the same. If the field is in perpendicular direction, there are three peaks in FMR spectra. Then, if you can say if we count the field from the perpendicular direction, every mode, including the first one, splits in many modes, and this is the resonance field versus canting angle. You can see the theory explains experiment, how to say, satisfactorily. Now we speak about thick rings. And to understand what is the difference between thin and thick rings, let's look at the FMR spectra of reference film. This is for thin film, this is for thick film. The difference is that here only one peak, which means only one mode. Here you can see 3 peaks. What does it mean? It means that for thick films, and also of course for thick rings, we should take into account not only in plane the dependence of spin wave profile from in-plane coordinates, but also the dependence from z coordinates. Now let's compare typical FMR diagram in perpendicular geometry for rings, for thin rings and for thick rings. It's perpendicular geometry, there are no splitting, you can see distinct standard spin this in peaks of standing speed wave modes. And the most important, that this is a usual dependence of intensity of this mode from the external field, or resonance field. It means larger field, larger intensity. Well, and when it's thickering, it's absolute mass. As you can see, here we have 4 peaks, and intensity doesn't monotonically decrease with decreasing field. What does it mean? It means the series I have an additional problem, additional headache, not only to explain the dependence frequency from the external field, but also I should explain this strange hierarchy of intensities. The explanation is just follows from the fact that profile of speed wave depends from Z coordinate. This is the effective Bias field. K is the wave vector along Z axis. Its exchange path depends such a way, and this increases with increasing number of modes. Then the dipolar field, vice versa, as my calculation shows that this field decreases with enhancing the number of modes or with enhancing the number of spin wave. So this interplay between dipolar term and exchange term leads to such dependence of intensity. This is theoretical. This is the theoretical calculation of intensity of these modes. This is experiment. As you can see, they agree quite well. And this is the external field versus frequency for 4 standing modes. Points are experiment, lines are series. So this also a theory fits experiment. Then, summary. We give a comprehensive investigation of spin wave dynamics in thin and thick ferromagnetic rings in saturated state. Our theory and experiment are in agreement. Thank you for your attention.
Some others,